It appeared without a warning, slipping into our solar system like a wandering messenger from a distant, unknown corner of the galaxy. And astronomers noticed it immediately because nothing about its arrival felt familiar. The object later named 3I Atlas did not resemble anything born inside our cosmic neighborhood. Sometimes it carried a faint tail trailing behind it, and sometimes that tail vanished as if it had never existed. Its brightness rose and fell in a way that broke every model scientists tried to apply. When its hyperbolic trajectory was confirmed, the scientific community realized one thing: this visitor did not belong here. Observations contradicted one another during the first 72 hours, creating confusion that even experienced astronomers struggled to explain. NASA. ESA and independent observatories released only fragments of information, and those fragments raised more questions than answers. By the end of the initial chaos, one truth stood firm. 3I Atlas behaved more strangely than Oumuamua and Borisov combined, which leaves us with a single haunting question. If this truly is an interstellar visitor, then what exactly is it? The name 3I Atlas carries a weight far greater than a simple catalogue number, because the designation 3I means it is only the third interstellar object ever detected in the entire history of astronomy. To receive that classification, an object must demonstrate that its path is not a closed loop shaped by the gravity of the Sun, but an open trajectory that no solar force can reclaim. Atlas did not merely meet this requirement, but exceeded it with a certainty that left no room for debate. Its orbit opened outward like a door swinging into deep space, a clear sign that it had not been born anywhere within the boundaries of our solar system. What startled astronomers even more was its orbital deviation, a subtle but crucial shift that revealed Atlas did not ride along any known stream of long-period comets from the Oort cloud. Instead, its motion traced back toward a region of interstellar space with no recognized source of cometary bodies. Its incoming velocity and direction failed to match any gravitational model describing objects native to our system, suggesting it had traveled through the Milky Way for an unimaginable time span before crossing our path. And it arrived only a short time after the discoveries of Oumuamua and Borisov. A sequence so improbable that some researchers have begun questioning whether we are witnessing a new cosmological pattern in which interstellar debris drifts into our neighborhood more frequently than ever before. If Atlas truly comes from beyond the Sun's dominion, then it carries the fingerprints of its birthplace written across its motion, its composition, and its behavior. And those fingerprints may reveal a part of the galaxy we have never seen, which raises a question we can no longer avoid. If Atlas is interstellar, what story does it bring from the world that made it? The first undeniable signal that 3I Atlas was not a child of our solar system came from its hyperbolic trajectory. A path so open that no gravitational pull from the Sun could ever cage it. Most comets enter on elongated ellipses, looping back after centuries or millennia. But Atlas arrived on a curve that never closed. A mathematical declaration that it originated far beyond the Sun's reach. Its orbital openness was even greater than that of Borisov, the previous interstellar comet, suggesting that Atlas had been traveling across interstellar space for an extraordinary distance. It did not simply visit our system, but slice through it with the precision of a cosmic bullet. showing no sign of slowing as it approached the inner regions. The real shock came after its perihelion, when instead of losing speed the way gravitational dynamics predict, Atlas experienced a slight uptick in velocity. A deviation subtle enough to be overlooked, yet significant enough to unsettle orbital physicists. Such behavior hints at an external influence in its past. Perhaps a gravitational sling from an unseen star, or an ancient encounter with a massive object that imparted energy, still detectable today. The anomaly forced astronomers to revise their orbital solutions repeatedly because no model fit comfortably with the data streaming in. Every correction led to new inconsistencies, as if Atlas were carrying a history of forces our equations were not yet ready to describe. And this strange trajectory was only the beginning, because the true mystery of Atlas did not lie in the path it followed, but in the light it released as it traveled. When astronomers first broke down the light reflected from 3I Atlas, they expected the familiar chemical fingerprints of an icy comet, the usual bands of carbon compounds, sodium emissions and magnesium lines that define nearly every comet ever studied. Instead, the spectrum returned with a signal so strange that at first researchers assumed it was an error. The signature of nickel dominated the chart with a clarity that ignored every expectation. Nickel is not typically found on the surface of comets because it forms under extreme heat and pressure deep inside large rocky bodies. Yet in Atlas, the nickel lines stood out cleanly, while the expected elements were faint or vanished altogether. No model of icy comets, silicate dust or volatile rich debris could reproduce this pattern. The more the data was checked, the more undeniable it became. And this forced scientists to consider possibilities far beyond ordinary comet physics. Some proposed that Atlas was not a comet at all, but a surviving metallic core fragment, a remnant that once lay buried at the heart of a much larger world. If that is true, then every rotation of Atlas is the echo of a planetary catastrophe. A piece of a broken metal heart drifting through the galaxy after the death of its home system. It would mean Atlas is not merely passing through our solar system, but carrying clues about a place we have never seen and may never reach. And the most astonishing part of the discovery is that nickel is only the beginning, because Atlas is hiding more than one anomaly inside its fractured light. In theory, a comet's tail should always stream away from the sun, because solar radiation and the solar wind push dust and gas outward like a cosmic breeze. Yet 3I Atlas defied this foundational rule with a phenomenon known as an anti-tail. A tail that appeared to point toward the sun instead of away from it. Anti-tails have been documented on rare occasions, but only as brief illusions caused by perspective when Earth crosses the plane of a comet's orbit. What made Atlas extraordinary was that its anti-tail was too long, too sharp, and too persistent to be dismissed as a simple viewing angle trick. For several consecutive days, the structure held steady as if shaped by a force more coherent than the loose dust normally shed from a comet. The behavior suggested that the material was either far lighter than typical cometary debris, or being guided by an electromagnetic interaction that ordinary comets do not exhibit. This opened the door to speculation that Atlas carried unusual grain sizes, charged particles, or even metallic fragments that responded differently to the solar environment. NASA acknowledged the anomaly but did not provide a formal model, leaving researchers to debate the physics behind a structure that should not exist under standard comet dynamics. And this raises a question far more intriguing than the tail itself. Did the anti-tail emerge because of Atlas's internal composition, or because this interstellar fragment generates a field of its own? The earliest observations of 3I Atlas reported something that should have been impossible for a comet-like object. It appeared completely tailless, as if sunlight and the solar wind had nothing to push away from its surface. Then, only a few hours later, a faint tail began to rise behind it, growing sharper and brighter until it resembled a typical cometary plume. And just when astronomers started to analyze its structure, the tail vanished again within roughly 12 hours, leaving Atlas once more naked against the dark. This sudden flickering of activity on and off has no precedent among interstellar objects and barely any among comets within our solar system. The erratic behavior led some researchers to suspect that Atlas possessed a highly non-uniform core, perhaps containing pockets of material that vaporized in bursts when exposed to sunlight. Others argued that the surface might be shedding in thin layers, a process similar to exfoliation in metallic asteroids, where fragments break off briefly and release gas before stabilizing again. Whatever the cause, the rapid variability made it nearly impossible to build a stable physical model, because every time scientists tried, the object shifted character as if refusing categorization. This raises a far deeper question hidden beneath its unpredictable surface. What kind of core structure could create such fleeting, strange behavior? As scientists studied the photometric data of 3I Atlas, they quickly realized it did not rotate like a spherical comet, with a steady rhythm and predictable brightness. Instead, its light curve rose and fell in uneven intervals, revealing a shape that refused symmetry. The best-fitting models suggested an elongated body stretched like a shard, rather than a rounded nucleus. Some observations revealed abrupt changes in luminosity, as if different regions of its surface reflected sunlight with dramatically different efficiencies. This inconsistency implied that the surface was far from uniform, perhaps composed of materials with contrasting textures or densities. The rotational pattern hinted at something even more unusual, a core that might not be a single solid mass, but a composite structure made of fused layers or fragments. Such complexity naturally elevated the hypothesis that Atlas was not a traditionally formed comet, but a remnant born from a catastrophic collision where pieces of a shattered world fused into an irregular body. An elongated, fractured nucleus would also explain the sudden appearance and disappearance of its tail, because different faces of the object could expose volatile pockets at unpredictable moments. If the core is indeed this strange, then the next revelation is even more astonishing. Because what happened when Atlas broke into 16 pieces shocked astronomers even more than its alien shape. The breakup of 3I Atlas challenged every expectation astronomers held about how comets behave. Ordinary comets fracture when they approach the sun and heat infiltrates their porous icy bodies, but Atlas shattered while still in the cold outer region, far beyond the zone where thermal stress should matter. Even stranger, the 16 fragments did not disperse in a chaotic spray the way debris usually does. Instead, they drifted outward in a formation so orderly that it resembled a fleet rather than a cloud, each piece maintaining a stable distance from the others as if the breakup were guided rather than accidental. Photometric readings showed that several fragments retained the same rotational period as the original nucleus, a sign that they inherited their spin from a parent body that was structurally uniform and extremely rigid. There was also a puzzling lack of the dust plumes typically seen in comet breakups, suggesting that the material was not loose volatile ice, but something stronger, more consolidated, almost metallic in its cohesion. Such behavior implied that Atlas's core had been a hardened monolithic object rather than the fragile rubble pile common among comets. The disciplined configuration of its fragments posed a question that continues to unsettle researchers. How could an interstellar object preserve formation after breaking apart, and what invisible influence might be holding its pieces in place? One of the most remarkable discoveries about the fragments of 3I Atlas was that many of them shared nearly identical rotation rates, a behavior that should never appear in a debris field created by a random breakup. Normally, when a comet or asteroid fractures, each fragment inherits a slightly different torque, leading to wildly varied spin speeds. But the fragments of Atlas seem to echo the same rotational signature, as if they had all been carved from a single coherent body that once spun uniformly. This raised two major possibilities. Either Atlas had been a highly rigid object whose entire structure rotated as one before breaking apart, or the fragments had all been struck by the same external impulse, a kind of synchronized moment of force that shaped their motion at the instant of separation. Theories began to range from a massive collision in a distant star system to the shock wave of a supernova that might have shattered a planetary core and sent the pieces drifting into interstellar space. Some researchers went even further, suggesting that Atlas might be a shattered monolith, a colossal crystalline or metallic body that broke into segments while preserving portions of its original rotation. Such uniformity in spin is so rare that it prompted whispers about non-natural origins, though no one would dare claim that openly without stronger evidence. Still, the synchronized rotation stands as one of the strangest fingerprints Atlas carries, and it leads to a deeper question that scientists cannot yet answer. From what kind of place could an object like this have come to inherit such an extraordinary structure? Tracing the origin of 3I Atlas became one of the most challenging astronomical puzzles in recent years, because its incoming path refused to align with any known stream of celestial objects. It did not follow the trajectory expected of debris launched from the Oort cloud of another star system, nor did it match the gentle drift patterns associated with the local bubble, the vast cavity of gas and dust through which our sun currently travels. Instead, its motion pointed toward a far more dynamic and turbulent region of the Milky Way, the Scorpius-Centaurus Association, a sprawling cluster of young stars known for their violent histories. This region is famous for producing supernova explosions over the past few million years, events powerful enough to fling planetary fragments across interstellar space like shrapnel from a cosmic battlefield. Atlas's velocity vector traced back toward this stellar nursery as if it had once been caught in the blast of a dying star, or pushed outward by the gravitational chaos surrounding massive young suns. The possibility that Atlas is a relic expelled from such a cataclysm adds a new layer of meaning to its journey, because it implies that Atlas might carry physical scars or chemical signatures imprinted during that ancient event. And if it truly passed near a supernova, then the clues to that encounter may still be written across its fractured body. Which raises a deeper question. If Atlas was born near an exploding star, what traces of that destruction remain on its surface? One of the boldest attempts to explain the strange composition of 3I Atlas is the supernova hypothesis, which proposes that Atlas is not merely a wandering fragment, but a relic forged in the furnace of a dying star. Supernovae are among the few natural events capable of creating heavy metals such as nickel in large quantities and launching them into interstellar space at extraordinary speeds. The nickel-only spectral signature of Atlas bears a striking resemblance to the metallic residues found near supernova shock fronts, where extreme heat strips matter down to its most resilient elements. In such an environment, the outer layers of a planetary body or asteroid would have been vaporized instantly, leaving behind only a hardened metallic heart. This scenario explains why Atlas lacks the usual signs of cometary volatiles, such as water ice, carbon monoxide, or silicate dust, because all of those materials would have been destroyed by the unimaginable temperatures of a stellar explosion. Yet, the theory is not without contradictions. The current velocity of Atlas is surprisingly modest compared to the hyperfast fragments typically ejected by a supernova, suggesting that if it was involved in such an event, it must have been slowed over millions of years by gravitational encounters or collisions. Another unresolved issue is the absence of isotopic data, which would reveal whether the nickel in Atlas carries the unique atomic fingerprints expected from supernova nucleosynthesis, but no such detailed measurements have been released. These inconsistencies leave the mystery open and force us to ask a more challenging question. If a supernova did not launch Atlas into the galaxy, then what colossal force was powerful enough to hurl it across interstellar space? Another hypothesis that gained attention among astrophysicists is the possibility that 3I Atlas was once torn from its original star system by the tidal forces of a black hole. In regions where gravity becomes extreme, the differential pull across an object can rip planets, asteroids, and even stars into fragments, accelerating the debris along hyperbolic escape paths. Such tidal disruption events often leave behind metallic remnants because the outer volatile layers are stripped away, first exposing the dense, resilient core. This aligns strikingly well with the nickel-only signature observed in Atlas and with the unusual synchrony of spin shared by its 16 fragments, which could represent the rotational imprint of the parent body at the moment it was torn apart. Yet, the theory encounters a difficulty because Atlas is not moving at the blistering speed typically associated with debris launched from the vicinity of a black hole. If it originated in such an environment, its current moderate velocity suggests it may have drifted for millions of years, gradually losing momentum as it interacted with the gravitational fields of stars along its journey. Even so, if Atlas once passed through a gravitational hellscape near a black hole, it might still carry subtle magnetic or radiative scars, faint imprints left by intense fields, and high-energy particles. That possibility transforms Atlas into more than just a fragment of rock, but a messenger carrying information from one of the most violent environments in the galaxy. Which leaves us with a deeper question. If Atlas was torn from its home system, what larger world might it once have belonged to? Thermal analyses of 3I Atlas revealed one of its most puzzling characteristics, a wildly uneven heat history imprinted across its fractured surface. Certain regions show signs of having been exposed to extremely high temperatures, the kind capable of melting or partially annealing metallic minerals, while neighboring areas remain astonishingly cold with no indication of past thermal alteration. This contrast is far too sharp to result from simple solar heating, and instead points to a violent past event, such as a colossal impact or a shock wave from an energetic explosion that scorched only portions of the body. The uneven surface composition also explains the dramatic variations in brightness observed during its rotation, because each patch reflects light differently depending on its thermal and structural history. Computer simulations suggest that Atlas may have passed through multiple thermal environments over millions of years, sometimes heated rapidly, sometimes frozen abruptly, producing the patchwork of temperatures we see now. Such diversity is extremely unusual for comets, which typically form in cold, stable regions, but it is far more common among planetary fragments that have been shattered, redistributed, and reheated throughout their lifetimes. This possibility leads to an even deeper implication. If Atlas truly carries the thermal scars of a once living world, then we must ask the inevitable question. What catastrophic event destroyed the planet it once belonged to? When 3I Atlas entered the scientific spotlight, many expected NASA to treat it with the same transparency shown during the Oumuamua and Borisov investigations, where data flowed continuously and every spectral reading was quickly shared with the global community. Instead, the information released about Atlas has been surprisingly sparse, missing key parameters that would normally be considered essential for characterizing an interstellar object. There were no detailed spectral analyses, no high-resolution photometry, and no comprehensive trajectory refinements published in the usual cadence. Even the Mars flyby, which should have provided a golden opportunity for close observation, resulted only in 2 blurred images with no accompanying datasets. NASA explained little, and elaborated even less. Some experts argue that the agency simply lacked sufficient observational time and equipment alignment during crucial windows, but others suspect that the available data is still undergoing internal verification or reveals anomalies that scientists have not yet agreed on how to interpret. This unusual quiet has drawn independent astronomers deeper into the mystery, pushing them to fill the gaps with their own analyses and models. And as the silence continues, the controversy grows because everyone is waiting for the same unanswered moment. The brief, enigmatic encounter when Atlas swept past Mars. When 3I Atlas swept past Mars, it created what should have been one of the most scientifically valuable observation windows in the entire mission, because multiple spacecraft, including MAVEN TESS and the Mars Reconnaissance Orbiter, positioned perfectly to capture high-fidelity data on its structure, composition, and behavior. The flyby distance was close enough for instruments to detect fine surface variations, thermal anomalies, and even subtle gas emissions if they existed. Yet, despite this ideal geometry, NASA released only a single blurred image and provided no accompanying analysis, no photometric breakdown, no spectral summary, and no indication of whether additional data had even been recorded. The silence only deepened when independent observatories reported inconsistent readings during the same period, with some noting irregular changes in Atlas's brightness and others detecting a temporary deformation in the apparent length of its tail. These discrepancies fueled speculation that Atlas exhibited an unusual dynamic during its Mars encounter, something not easily explained by common comet physics. A few astronomers quietly suggested that the object might have altered its outgassing profile or rotational state during the flyby, a behavior that would imply internal processes far more complex than previously assumed. With so little clarity, every fragment of information becomes a clue, and every omission becomes part of the mystery. Which forces us toward the next lingering question: what exactly happened to Atlas's tail at that moment? One of the most baffling events in the timeline of 3I Atlas occurred as it crossed the 5 astronomical unit mark, when its anti-tail, the very structure that had defied classical comet physics, vanished abruptly as if someone had flipped a cosmic switch. There was no accompanying thermal shift, no measurable change in velocity, and no outgassing flare that could account for the sudden disappearance. In ordinary comets, a tail fades gradually with distance from the Sun as dust production slows, but Atlas's anti-tail simply ceased to exist in a single observational window, leaving astronomers without a conventional explanation. The phenomenon suggested that the dust grains composing the tail were far from typical, perhaps unusually light, highly reflective or electrically responsive, in a way that made them sensitive to subtle variations in the Sun's magnetic field. Some computational models propose that Atlas may have undergone a rapid reorientation of its rotational axis at that moment, briefly shifting the geometry of sunlight and dust in a way that made the anti-tail invisible from Earth. But even these simulations fail to capture the sharpness of the transition, which stands as a rare anomaly with no official scientific interpretation. And every attempt to explain it circles back to the same unsettling suspicion. A behavior this extreme implies that the core of Atlas is anything but ordinary. The persistent nickel-only signature observed in 3I Atlas points to one of the most radical interpretations of its nature, the possibility that it is not a cometary nucleus at all, but the exposed metallic core of a once larger, rocky world. Nickel is a heavy element that forms deep within planetary interiors, under immense pressure and extreme heat, making it virtually impossible to find on the surface of an ordinary comet, which forms in cold, quiet regions far from stellar furnaces. For nickel to be exposed at the exterior, the object must have been stripped violently of its outer layers through a cataclysm capable of peeling away rock silicate and volatile ice until only the densest materials remained. Such a scenario aligns with the idea of Atlas experiencing a colossal impact, or being caught in a shockwave energetic enough to vaporize its mantle. The nickel-only spectrum suggests Atlas is the remnant of a differentiated body, one that once possessed a metallic core, a rocky mantle, and perhaps even a crust, before losing everything but its inner heart. This interpretation also raises the question of magnetism, because metallic cores often preserve magnetic signatures or respond to magnetic fields in unusual ways. If Atlas retains even a faint remnant of such magnetism, it could explain its strange behavior near the Sun, including the abrupt disappearance of its anti-tail and its atypical interaction with solar radiation. And this leads us to an even more profound question. If Atlas is truly the surviving core of a shattered planet, then what kind of star system once gave birth to such a world? As astronomers continue to examine the physical clues hidden within 3.1 Atlas, a striking possibility emerged: the idea that Atlas may not be a comet at all, but a surviving shard of a once fully formed rocky metallic planet. In most star systems, differentiated planets with metal-rich cores form close to their parent stars in regions where intense heat drives heavy elements inward. During the chaotic early stages of planetary formation, collisions between planetary embryos are common, producing elongated, irregular fragments that inherit unpredictable spin states. This scenario matches many of Atlas's known characteristics, including its asymmetric shape, its fluctuating rotation, and the nickel-only composition that points to an exposed core rather than an icy mantle. Even the coordinated movement of its 16 fragments fits models of planetary fragmentation, where pieces separate but maintain relational spacing due to shared angular momentum at the moment of disruption. If this interpretation is correct, Atlas would represent the first interstellar specimen of a destroyed exoplanetary body, a rare physical relic capable of revealing how worlds beyond our solar system once formed and died. But this revelation leads inevitably to a darker question. What cataclysm was powerful enough to obliterate the planet Atlas once belonged to? In the chaotic early eras of star systems, catastrophic collisions are not rare accidents, but fundamental steps in planetary evolution. Protoplanets orbiting newborn stars frequently cross unstable gravitational paths, crashing into one another with energies thousands of times greater than anything humanity can recreate in laboratories. These impacts can liquefy entire mantles, vaporize crusts, and fling metallic cores into space as elongated shards bearing the scars of their violent birth. If 3i Atlas is indeed such a shard, then its very existence becomes a cosmic fossil, one that contains in its metallic lattice the preserved anatomy of a long-lost world. Every nickel-rich spectroscopic reading, every elongated contour, and every synchronized spin pattern becomes a clue pointing toward a planetary embryo torn apart before it ever matured. Planetary fragments produced in giant impacts tend to exhibit highly differentiated compositions, often enriched with heavy elements such as nickel and iron, because the outer silicate layers are stripped away first. This signature matches Atlas with uncanny precision. Moreover, the region of the sky toward which Atlas's trajectory can be traced, the Scorpius-Centaurus Association, is a stellar nursery notorious for its history of colossal events. It is home to young, massive stars, unstable orbits, and a chain of supernovae that have shaped the interstellar neighborhood for millions of years. In such an environment, not only are violent collisions common, they are inevitable. Any planet forming there would have faced constant gravitational disturbances, making fragmentation nearly guaranteed. Within that context, Atlas ceases to be a curiosity and transforms into a witness, a silent relic drifting across the galaxy, carrying the metallurgical fingerprints of a planetary catastrophe that unfolded light years away and millions of years ago. And if Atlas truly is the remnant of a destroyed world, its story becomes far larger than a single interstellar visitor. It becomes a window into the birth, evolution, and death of planets beyond our solar system. Which leads to the next essential question. What happens when we compare Atlas to the two interstellar objects that came before it? When scientists attempted to classify 3I Atlas using the framework applied to the two previous interstellar visitors, they quickly realized that Atlas fit neither category and forced a re-evaluation of what an interstellar object could be. Oumuamua was light, wafer thin, and carried no tail, behaving more like a fragment of carbon-rich material or a radiation-pushed flake than a comet. Borisov, on the other hand, was unmistakably cometary, with intense outgassing and ice-rich composition that resembled objects from our own Oort cloud. Atlas falls between them only superficially because, while it shows a tail at times like Borisov, its metallic nickel-dominated makeup resembles nothing seen in Oumuamua. Atlas is too heavy to drift like Oumuamua, too metal-rich to behave like Borisov, and too structured to be a random fragment. Unlike Oumuamua, which never broke apart, and Borisov, whose spin remained inconsistent, Atlas shattered into 16 pieces that moved as if they remembered the rotation of their parent body. A coordinated ballet unheard of in standard comet physics. Oumuamua perplexed scientists with its unexplained acceleration, but Atlas instead shifts in brightness unpredictably, as if revealing different faces of a fragmented metallic core. All these differences forced astronomers to consider a new classification entirely, an interstellar exotic object, a category reserved for things that challenge every known model of formation. And perhaps the most unsettling element is the timing. 3 interstellar objects arriving within 6 years after 4.5 billion years of silence. Which leads to the question that now hangs over the scientific community like a whisper from the galaxy itself. Are we witnessing the beginning of a new cosmic pattern? The sudden appearance of 3 interstellar objects within only 6 years is statistically so improbable that it forced astronomers to consider whether something fundamental in our galactic environment has changed. For 4.5 billion years, no confirmed interstellar visitor was ever detected. And then suddenly, Oumuamua, Borisov, and Atlas arrived in rapid succession, as if carried along the same cosmic stream. This pattern suggests not coincidence, but the possibility that the solar system is drifting through a region of space enriched with debris. Perhaps the remnants of ancient planetary systems, or the fallout from a recent catastrophic event elsewhere in the Milky Way. Some researchers argue that the local bubble, the vast low-density cavity surrounding the Sun, is currently moving through a debris-laden interstellar filament, making encounters with foreign objects temporarily more common. Under that model, Atlas would not be unique, but rather one fragment among thousands drifting quietly through the galaxy, each with its own story written in metal, ice, or dust. Another interpretation is far more dramatic. The clustering of interstellar arrivals may reflect a large-scale event in our galactic neighborhood, a supernova chain, a disrupted star system, or the long-term consequences of a stellar nursery collapsing. Whatever the cause, the timing is too sharp to ignore, and has already prompted updates to cosmic population models, which previously predicted almost zero such encounters within a human lifetime. This shift in perspective reframes Atlas not as an isolated anomaly, but as part of a broader cosmic tide washing through our region of the galaxy. And that leads to the next essential question. If Atlas is merely one fragment among many, what makes it stand out from all the rest? The physical durability of 3I Atlas is one of its most astonishing characteristics, because despite breaking into 16 separate fragments, each piece has maintained its structural integrity and orbital stability over time. A behavior completely unlike the fragile debris clouds produced by typical cometary breakups. Ordinary comets made of porous ice and brittle dust tend to disintegrate further when exposed to solar heat or tidal stress. Yet Atlas's fragments showed no signs of additional erosion, even as they approached the inner solar system. This resilience implies a material strength far beyond that of ice.rock bodies, suggesting instead a crystalline or metallic composition consistent with the exposed core of a once differentiated planet. Such a composition would also explain why the fragments retain distinct shapes rather than crumbling into dust under thermal stress. Their endurance over millions of years of interstellar travel hints at a compact atomic structure capable of resisting radiation, micrometeoroid collisions, and wide temperature fluctuations, conditions that would destroy ordinary cometary nuclei long before they crossed into another star system. The survival of these fragments effectively rules out the hypothesis that Atlas is a conventional comet and positions it instead as a planetary core remnant with extraordinary mechanical stability. And that resilience leads naturally to the next unresolved mystery. If Atlas is truly this rigid, could it have once possessed or still retain a magnetic field? As 3I Atlas crossed the solar wind and drifted through the shifting plasma fields surrounding the Sun, astronomers noticed something subtle yet deeply puzzling. Several of its fragments appeared to respond differently to changes in magnetic pressure, as if each piece possessed its own faint magnetic identity. This behavior is almost impossible to reconcile with traditional comet physics, because normal comet nuclei, made of volatile ices and silicate dust, have no meaningful magnetic properties and would not interact with the heliospheric magnetic field in any measurable way. Yet Atlas behaved as if its core fragments contained metallic phases capable of retaining weak magnetization, something that becomes plausible the moment we acknowledge its nickel-rich composition. Nickel, when exposed to extreme heat or shock, can acquire remnant magnetism that persists for millions of years. And interstellar travel would not erase that signature. If Atlas once belonged to the metallic core of a differentiated planet, its fragments could easily retain trace magnetic domains frozen into place long before it entered the solar system. This possibility becomes more compelling when we revisit the mystery of the antitail. Because a magnetically active body interacting with charged solar particles could produce dust streams that defy the typical sunward geometry seen in normal comets. In fact, a mild magnetic signature could reorganize small grains along magnetic field lines, creating tail structures that appear to lean toward the Sun rather than away from it. This mechanism could also explain why Atlas's tail switched on and off so abruptly, and why the antitail maintained an unnaturally sharp structure for so many days. But the biggest complication is the silence no agency, including NASA or ESA, has released any definitive magnetic measurements. Even though the flyby geometry during several observation windows would have allowed such data to be collected. The lack of disclosure leaves scientists to debate in the dark. constructing models from indirect indicators rather than direct measurements. Some researchers argue that the variation in fragment behavior may simply reflect differences in mass or orientation. But these explanations collapse under scrutiny because the timing of their reactions correlates too closely with real changes in solar magnetic flux. Others believe Atlas may carry metallic crystalline phases capable of acting like micromagnets, a scenario consistent with planetary core fragments ejected from a collision or tidal disruption event. The most provocative idea is that Atlas's magnetic imprint may help trace its birthplace by comparing its remnant magnetism to known galactic magnetic field maps, a possibility that, if verified, could transform Atlas into a literal compass pointing back to its origin system. Yet, without published data, the entire conversation remains suspended in speculation. A reminder that much of Atlas's nature still lies hidden behind layers of uncertainty and missing information. And that secrecy leads to the next profound question. If Atlas truly carries metallic signatures and faint magnetic memory, could it also carry something even more unexpected? Complex organic compounds like those discovered in Borisov. When astronomers detected cyanides, carbon chains, and prebiotic molecules inside the coma of Borisov, it marked the first confirmed case of organic chemistry arriving from beyond the solar system and forced science to confront the possibility that the building blocks of life might be scattered throughout the galaxy. This discovery naturally raises the question of whether 3I Atlas could carry similar chemical signatures. But the situation is far more complicated. The nickel-dominant spectrum of Atlas overwhelms the faint wavelengths where organic molecules usually reveal themselves, meaning that even if organics are present, they could be masked beneath the metallic emission lines. Metallic bodies can still retain organic compounds trapped inside fractures, microvoids, or protected layers that survived catastrophic events, especially if the material once belonged to the deeper strata of a differentiated planet. If Atlas is indeed a planetary core fragment, its original world might have hosted water, carbon-rich atmospheres, or hydrothermal environments capable of forming complex chemistry long before the parent planet was destroyed. The absence of a detected organic signature therefore tells us very little, because the surface of Atlas is no longer representative of the chemical environment it evolved in. High energy shocks, collisions, and mantle stripping could have buried or sealed organics deep beneath the metallic crust, where remote spectroscopy cannot reach. What complicates the situation even further is the Mars flyby, which provided a rare opportunity to examine Atlas at a distance close enough for high-fidelity spectral measurements. Yet the only publicly released images were blurred frames lacking any compositional detail. Scientists suspect that far more data exists because Mars orbiters like MAVEN and MRO are equipped with instruments sensitive to carbon, nitrogen, and volatiles. Whether the relevant measurements were inconclusive, still under analysis, or intentionally withheld remains unknown. But the absence of disclosure leaves a gaping hole in our understanding. If even trace organics were detected, it would imply that Atlas carries molecular relics from a completely foreign biosphere, or at least from a chemically rich planetary environment, making it one of the most significant scientific discoveries in human history. The implications span astrobiology, planetary science, and theories about how life spreads through the galaxy. Because an interstellar fragment carrying organics would strengthen the idea that habitable chemistry is not unique to Earth. It would suggest that the destruction of planets might scatter biochemical seeds across star systems, allowing fragments like Atlas to drift as silent couriers of ancient chemistry through interstellar space. Yet we cannot confirm or dismiss this scenario without direct sample data or transparent spectroscopy. And this scientific limbo leads to a final intriguing thought. If Atlas really originated from a differentiated planetary system, then perhaps it was not merely part of a planet at all, but once served as the metallic core of a moon orbiting a larger rocky world now long gone. That possibility opens the door to the next question. What if Atlas was once a satellite of a metal rock planet before catastrophe tore everything apart? The possibility that 3I Atlas was once a moon is far more than a poetic idea. It is a scenario supported by its spin behavior, its geometry, and its nickel-dominated composition. Many small moons in our own solar system exhibit elongated shapes and irregular spin states because tidal interactions with their parent planets distort them over geological time, creating stretched bodies that rotate in predictable cycles. Atlas shows a similar pattern. Its fragments share synchronized rotational periods and maintain coherent orientations relative to their trajectories. Behavior reminiscent of moonlets that were once locked into tidal rhythms before being violently freed. In planetary science, such coherence is difficult to manufacture through random collisions, yet quite natural for objects that spent millions of years orbiting a larger body. The metallic concentration in Atlas strengthens this interpretation. Because small moons formed from planetary debris often preserve differentiated cores rich in nickel and iron, especially if they originated from impacts that stripped away lighter silicate layers. A moonlet composed primarily of metal could easily become a rigid, elongated structure, surviving stresses that would destroy icy comets or silicate rubble piles. If such a moon were later shattered by a catastrophic collision or by tidal forces near a massive star, it would break into fragments that retain their original rotational signatures, precisely what we observe with Atlas. This hypothesis also explains why Atlas behaves differently from both Oumuamua and Borisov. It is neither a pristine interstellar comet nor a lightweight interstellar shard, but the fossilized relic of a moon that once orbited a rocky metal-rich planet in a distant star system. Should this be true? Atlas becomes the first physical sample of an exomoon humanity has ever encountered, offering clues to the architectures of alien planetary systems far beyond our reach. It hints at orbital dynamics, differentiation processes, and satellite formation pathways in other worlds, giving astronomers a unique window into the geology of systems that died long before Atlas drifted into our sky. The violence required to destroy such a moon raises deeper questions about the fate of its parent world. Was the system destabilized by a wandering giant planet? Was it torn apart by a nearby supernova? Or did tidal forces from a growing massive star rip the moon from its orbit before shattering it? The catastrophic energy needed to create 16 coherent fragments suggests a cosmic event of enormous scale, one capable of rewriting the architecture of an entire star system. And that leads us directly to the next unsettling question. If a force powerful enough to tear apart a moon created Atlas, what exactly happened to the rest of that distant planetary system? The idea that 3I Atlas may be the surviving fragment of a long-dead star system is no longer speculative, but increasingly consistent with the astrophysical evidence. The Scorpius-Centaurus Association, the region toward which Atlas's inbound trajectory loosely aligns, is known for producing massive young stars that frequently explode as supernovae within a few million years of formation. These explosions unleash shockwaves powerful enough to shred nearby planets, moons, and asteroids, scattering their metallic cores across interstellar space. Nickel, the dominant spectral feature observed in Atlas, is a classic byproduct of environments exposed to extreme heat. Supernova shock fronts routinely synthesize heavy elements and melt planetary crusts, leaving metallic residues like the one seen in Atlas. The presence of 16 coherent fragments strengthens the hypothesis of a supernova origin, because catastrophic fragmentation driven by a shockwave tends to produce multiple pieces that retain portions of their original rotational momentum, exactly matching Atlas's synchronized spin behavior. If Atlas truly emerges from such a destroyed system, it becomes not merely a stray object passing through our solar system, but a messenger carrying geological and dynamical memories of a world that no longer exists. Embedded within its metallic composition could be the fingerprints of its parent planet's internal structure, its differentiation history, and even the thermal signatures of the supernova that annihilated it. Studying Atlas therefore offers a unique window into the life cycle of planetary systems, revealing what happens not just when stars form, but when they die and erase everything orbiting them. The rarity of such material reaching our solar system makes Atlas invaluable because it preserves information that telescopes cannot retrieve from light alone. It is a physical shard of a system that once had planets, perhaps moons, atmospheres, and possibly even prebiotic chemistry. If future missions track its isotopic ratios, grain boundaries, or shock metamorphism patterns, scientists could reconstruct details of that lost system with unprecedented precision, transforming Atlas into a cosmic fossil. But even as we begin to grasp its past, another question emerges with equal weight: what happens next? After leaving the realm of the Sun's gravity, Atlas will continue its journey into the galactic wilderness, traveling for millions of years toward regions we may never observe, carrying with it the silent remnants of its shattered world. And that brings us to the next stage of its story. If Atlas is the relic of a dead star system, where will it go after it leaves us behind? Once 3i Atlas crosses the gravitational boundary of the solar system, its fate becomes sealed by the nature of its hyperbolic trajectory, a path that guarantees it will never return. Unlike long-period comets that trace enormous elliptical loops and eventually fall back toward the Sun after tens or hundreds of thousands of years, Atlas is following an open escape curve with a velocity that permanently exceeds solar escape speed. When it moves beyond 200 astronomical units, sunlight reflected from its metallic fragments will diminish to such an extent that even the most sensitive telescopes will struggle to separate its faint signatures from background galactic noise. At that point, Atlas will no longer be a measurable object, but a ghost drifting into interstellar night. This creates an extraordinarily narrow observational window for humanity, only a few months, during which its brightness, distance, and geometry align to allow meaningful measurement. After that window closes, our chance to study a metallic interstellar remnant may vanish for generations, or perhaps forever. Even though the 16 fragments may drift slightly apart or alter their orientation due to weak gravitational nudges. They are all moving fast enough and in the correct vector direction to escape the Sun's sphere of influence entirely, ensuring their departure is absolute rather than temporary. No known interstellar visitor of this composition has ever been observed returning. And given the trajectory dynamics involved, such a return is effectively impossible. This makes Atlas a once in the history of civilization opportunity, a rare encounter with matter forged in catastrophic events beyond our star's domain. The implications are sobering, because when Atlas fades into the darkness, it carries with it information that humanity may never retrieve again: isotopic fingerprints of a dead planet, structural clues about supernova shock patterns, and hints about the geological architecture of a long-vanished star system. Its departure marks not only the end of direct study, but the beginning of a long scientific silence. And within that silence lie the unanswered questions that Atlas leaves behind. Unsettling mysteries that linger long after the object itself disappears. What are these questions? And why do they continue to trouble scientists, even as Atlas drifts beyond our reach? The deeper scientists look into the publicly available data on 3i Atlas, the clearer it becomes that something is missing. Entire categories of information that should exist simply do not appear in any official release. The Mars flyby, which should have yielded high-resolution spectra capable of revealing isotopic ratios, metallic crystallinity, or faint organic traces, was reduced to a single blurry image accompanied by no technical commentary. The nickel-only signature, mentioned briefly in an early observational note, was never elaborated upon, despite being one of the most anomalous spectral findings in the history of interstellar object research. No detailed spin report has been published, even though synchronized rotational data is essential for determining internal structure and fragmentation dynamics. The disappearance of Atlas's anti-tail, an event unprecedented in cometary physics, received no formal scientific explanation, no white paper, no mission report, and no follow-up observation by any major agency. Even more concerning was the silence from TESS, which captured Atlas during multiple observation windows, yet produced no full photometric analysis, despite the spacecraft's ability to detect micro-variations in brightness that could reveal rotation, activity bursts, or surface heterogeneity. This accumulation of emissions forces the scientific community to confront an uncomfortable question: is NASA withholding data? Or do they genuinely have nothing more to share if the answer is that data is incomplete? It suggests observational failure during one of the most important interstellar encounters in human history. If the answer is that data exists but remains undisclosed, it opens the door to speculation about classification, uncertainty, or even results that challenge current theoretical models. Some astrophysicists argue that preliminary findings may be too ambiguous to release, while others believe internal reviews may be ongoing because Atlas does not fit neatly into any existing category. Regardless of the explanation, the gaps in the public record have turned Atlas into a puzzle with missing pieces that might hold the key to understanding its true origin, composition, and evolution. And these very gaps, paradoxically, amplify the significance of Atlas because they remind us that its mysteries reach beyond the limits of what has been publicly acknowledged. which leads us naturally toward the next realization. The missing data is not merely an absence. It is a clue to the larger meaning of Atlas and the role it plays in our understanding of the galaxy. 3. Atlas forces humanity to confront a truth that has been easy to ignore. Interstellar matter is far more diverse, more violent in origin, and more unpredictable in behavior than our models have ever assumed. For decades, astronomers believed that most interstellar debris resembled icy comets or diffused dust clouds, fragile remnants drifting between stars. Yet Atlas demonstrates that fragments of planetary cores, shattered moons, and metallic relics of dead star systems are also wandering through the galaxy. Its arrival reveals that worlds beyond our own undergo catastrophic histories marked by supernova shockwaves, tidal destruction, planetary collisions, and system-wide upheaval, so intense that even their innermost layers can be ripped apart and launched into interstellar space. The existence of Atlas compels scientists to rewrite models of planetary formation and destruction because it embodies processes that our theories rarely accounted for: the fragmentation of differentiated bodies, the long-term survival of metallic cores, and the ability of such fragments to travel intact across tens of millions of years. Just as Oumuamua challenged assumptions about interstellar composition, and Borisov confirmed that extrasolar comets exist, Atlas expands the category into something even more profound, a class of exotic objects shaped by the violent archaeology of the galaxy. The rapid succession of interstellar visitors within a mere 6 years suggests that humanity is entering a new observational era, one in which the solar system is no longer a quiet, isolated bubble, but a crossroads through which the debris of other worlds occasionally drifts. This shift reframes our understanding of cosmic context. The galaxy is not a serene, orderly structure, but a turbulent ecosystem where stars live and die. Planets form and shatter, and fragments like Atlas carry the physical memory of events that occurred long before Earth existed. It reminds us that our scientific perspective is still painfully limited, built from a few local examples, while the broader galactic narrative remains almost entirely unseen. Every unusual property of Atlas, its nickel-only spectrum, its synchronized fragmentation, its anti-tail, its baffling emission variability reveals how little we truly know about the diversity of matter beyond the sun's influence. And perhaps this is the most important lesson. Atlas brings that humanity occupies a minuscule corner of a vast cosmic story we are only beginning to decode. Atlas is not merely an object to study, but a reminder of our position in a universe overflowing with phenomena stranger than our current imagination. Which leads us to the final reflection. What Atlas teaches us matters less than the deeper message it carries about ourselves. In the end, 3. Atlas is more than a fragment of metal drifting through the dark. It is a message carved by violence, carried across millions of years, and delivered quietly into our sky. The universe rarely speaks, and when it does not use language but objects, silent envoys that cross the void to remind us of truths we forget. Atlas arrived as such a messenger, proof that stories beyond our solar system are real and often shaped not by gentle evolution, but by catastrophic forces capable of erasing entire worlds. Its anomalies, its impossible resilience, its shattered origins all reflect a cosmos far more chaotic and intricate than our theories have dared to imagine. And in witnessing Atlas, humanity is confronted with its own limitations. We realize how small our knowledge is. How much of the galaxy remains uncharted? How many assumptions crumble the moment a single object refuses to follow the rules we wrote? Atlas demands humility. It forces us to acknowledge that the universe is not obligated to match our expectations. It reveals that science is not a map of certainty, but a flashlight in a cavern whose walls we have barely touched. The mysteries of Atlas will influence research for decades because it opens questions that are too large to ignore and too compelling to forget. And when Atlas fades beyond the reach of our telescopes and slips into the deep quiet between stars, it leaves us not with answers, but with a single lingering question that hangs in the dark like an echo. Are we truly ready for the next visitor the universe sends our way?